In an earlier video, I said I'd be reviewing some of the MERG DCC model railway kits available from the members only kit locker. In this video, I'll be looking at 3 kits, including a DCC command station, a handset controller and an RJ22 connector kit. This provides a way of controlling model railway DCC locomotives and accessories using CBUS and a homemade controller. Generally, the kits are fairly straightforward, but the handheld controller is significantly more challenging to solder. I'm fairly proficient with a soldering iron and I found some of it difficult, although it shouldn't be beyond the abilities of most. There is an alternative if you're interested in computer control, and I have got the USB CBUS adapter kit, and I'll be covering that in future video, so please subscribe if you're interested in seeing that. This diagram gives an overview of the MERG CBUS DCC track control system. I'll cover the controller later, but for now I'm going to start with the DCC command station, which provides the power and signals to the track. Or there is an optional buffer for larger layouts, which can be used when there's need for a higher power capability. I bought the USB interface kit as part of the CBUS Beginners Kit 102B, which also includes some other modules, and I'll be covering that at a later stage. Starting with the DCC command station, kit number 91A. The kit involves soldering components onto a supplied PCB. In the kit is the PCB and all the components needed and a set of instructions. You just need some standard electronics tools and your own solder. The kit includes good step-by-step instructions for installing the components. I suggest reading through each section fully before starting, but it's fairly comprehensive. It provides an explanation of some of the components. It does not provide a full explanation of how the overall circuit works, and I'll hopefully provide that later in this video. There's another guide available to download from the MERG knowledge base, which covers the steps in more detail and using simple images, although the printed sheet should be sufficient. The soldering was fairly straightforward. There are quite a few components, so I wouldn't recommend it for your first ever attempt at soldering, but for anyone that has successfully soldered a kit previously, then it should be okay. After installing all the components, it provides some steps for testing prior to connecting the integrated circuits, and further testing after adding them. I did come across a couple of minor issues at this stage, but this was due to my setup rather than any problem with the kit. Let me explain. I used my bench power supply for the initial testing, and I set the bench power supply to the suggested voltage of 15 volts DC, but I also set it with a low maximum current for the overcurrent protection. I think I set it at around 500 milliamps. I thought that would be enough. After all, I'm not even connecting it to the track, let alone to a locomotive at this stage. When I powered on without the ICs in place, I did all the voltage checks suggested and the values were all as expected. When I powered the board after connecting the integrated circuits, then nothing worked. Even the LED that lit during the earlier stage of testing didn't light. I realised it was tripping my bench power supply. I suspect it was due to the inrush current when first charging the capacitors. Something I had encountered before with the same power supply when used on my own capacitor discharge unit circuit design. So I needed to increase the overcurrent protection. I set that to 1 amp. When in use, I'll probably use at least 3 amps power supply. After increasing the overcurrent protection, the board powered on as expected. It used only a small amount of current once it was powered on, less than 100 milliamps, with the controller connected, so I'm pretty sure it was just an inrush when it was charging the capacitors. I followed the voltage tests, which were mostly within the expected range. But one of the tests is to test the output of the track power connector with a multimeter looking for an AC voltage. I used my normal better quality multimeter, which auto senses AC and DC. But in this case, it read a really low DC value, as though the circuit wasn't working. Now the track power is technically not an AC supply. It's actually a PWM, pulse width modulation signal, which goes positive and negative, also known as bipolar DC. And therefore the auto sensing multimeter detected that as DC, and as its sample rate is clearly much less than the output, it gave a really small reading. Swapping to my older multimeter, which has a manual select between DC and AC, gave the expected readings of over 12 volts. So that all appears to be working fine, but it did cause a bit of confusion at first. If you want an accurate voltage reading, then you could use a true RMS meter or connect an oscilloscope, but that's probably overkill for this basic check. Now, it's not actually possible to test beyond that until I have one of the CBUS modules able to send the appropriate commands to the DCC command station. So I left the testing at that stage and moved on to the next module. I later connected it to a model railway after physically disconnecting the previous DCC controller first. One challenge is that I used a thick gauge of wire using 0.75mm squared cable. This is good from the point of view of having a low resistance, but I struggled a little with connecting it to the small terminal connector on the PCB because it was such a small size. The booster kit could also be used, which would connect better to a thick gauge wire. I also needed a controller and the RJ22 board. I'll explain about those later, but for now I'll just say that they or an alternative is needed before you can actually run any model trains with the command station. When I placed a DCC locomotive on the track, I was able to control it using the handheld controller, but I'll explain that in more detail later. Here's a bit of an explanation about how the circuit actually works. As I said, it isn't really explained from the instructions, although the instructions do say what some of the ICs are, and it does provide a schematic circuit diagram. As most of this is fairly standard electronics, I'm just going to have a go at explaining how it works, just based on the diagram. And this is just my initial view, so if you spot anything I get wrong, please leave a comment below. So starting with the top left of the diagram, the power is coming in with a diode used to protect against reverse voltage. These three ICs across the top are all common linear regulators. IC7 and IC2 are 78 series regulators, the last two digits representing the output voltage. So, with a 15 volt input, the 7812 gives a 12 volt output, and then this 7805 drops that to 5 volts for the internal circuitry. There's an optional jumper, LK2, which can be used to supply power to other modules. The LM317T is a variable voltage regulator, and the output can be set using the variable resistor. This allows for changing the traction voltage that's sent to the track. Continuing on the diagram from left to right, the CBUS connector on the left connects to the MCP2562. This is a CAN bus transceiver. It ensures the bus is at the correct voltage and tolerances and provides protection against voltage spikes or short circuits. There is another connector shown which goes to header pins on the PCB. That connects the same pins as the status LEDs. Initially, I thought this may be a way of providing LEDs off the board, but I see it has a FLIM configuration option, so it appears to be a programming interface. It also appears to be a common interface for other MERG CBUS modules. The main block in the centre of the diagram is a PIC integrated circuit. So what is a PIC? It's a microcontroller, like those you may have seen on an Arduino or a Raspberry Pi Pico. In fact, PIC usually refers to the brand of the microcontroller, like how Atmel AVR chip is commonly used in the standard Arduinos. The PIC uses a different architecture, and they're often programmed externally before adding to a circuit, whereas an Arduino includes the circuitry to program it by just connecting via USB. Although you could program AVR chips externally, and you can program a PIC in circuit using an in-circuit programmer. Essentially, the PIC is the brains of the circuit. It handles all the inputs and generates the waveform needed to provide a DCC output. It needs some external components to work, and mainly the crystal oscillator with a pair of capacitors, which is used to generate a clock signal required by the PIC. The L6202 is the traction driver IC. It's a full bridge driver IC designed for controlling motors, but in this case is used to provide a DCC output which can alternate in polarity. The The IC at the top is an MC4426YN, referred to as a booster interface driver. The MC4426 is a MOSFET driver designed to provide a suitable signal for sending to the optional DCC booster board. There are a few other components on the board. For example, there are capacitors next to each of the ICs, which are the decoupling capacitors used to prevent noise from one part of the circuit from disrupting other parts. But pretty much that's the circuit. The command station needs something to give instructions, and this is most commonly some form of handset. MERG provide two kit options. They're very similar, but one uses a potentiometer for the speed control, giving an absolute position of the knob to represent the speed, and the other is based around a rotary encoder, which measures the relative position of the knob. The one I bought is the handset with the encoder, known as the CAN CAB2E. The kit is a bit more complicated than the command controller. It starts with some modifications needed to the plastic enclosure, but that's not too difficult. It's a bit different to the usual soldering. The soldering starts off okay. It's a bit more complicated as the components need to be soldered on both sides of the board, and there are also some components that are very close to each other, making soldering a bit more challenging, and this is all due to the compact nature of the handset. So whilst this part is a bit more complicated than other PCBs, it's not too difficult at this stage. The most difficult part comes with soldering the LCD display. The connector is tiny, and this is the nature of the display that has such a fine connector. This is acknowledged in the instructions, and the kit even includes a small amount of desoldering braid which can be used to remove solder bridges that may happen as you're doing the soldering. Despite having a lot of experience with soldering, I used all the desoldering braid and then a little bit more. I also used some flux to help the braid to absorb some of the solder. It's not necessarily the most difficult soldering I've ever done, but it's much harder than typical soldering. I don't want to put people off getting the kit, but I wouldn't recommend it for beginners. I would recommend getting practice with the kits first. Then, when soldering the display, just take your time and make sure you remove any solder bridges before you do any testing. Best way is to check with a magnifying glass, just to make sure there are no solder bridges that are not obvious to see. It's a shame that the handset wasn't made a bit bigger. Some handsets are much bigger, although I can see pros and cons for either way, especially when turning it into a kit. Once again, the instructions include some tests, although the PCB was needed with the RJ22 connectors first, as well as the command station that I've already mentioned. I'll explain the initial test at this point, even though you'd need to first put that other PCB together. The tests involve connecting the handset to the DCC command station and running through the process of issuing instructions as though controlling the train. This shows that the handset is communicating with the command station correctly, and it also shows that the correct commands are being shown on the LCD display. As before, I'll take a quick look at the schematic circuit diagram and an attempt at explaining how this likely works. Starting at the bottom left, this is where the CBUS connection is made, using the RJ22 connector. It connects to an MCP2561 or MCP2562 CAN bus transceiver. The 12 volt input from CBUS also goes through a diode to a 78L05 voltage regulator to provide a 5 volt power supply for the ICs. This is similar to the 7805 used in the DCC command controller, but is a lower power version, so just providing enough power for the components on the handset. Again, most of the electronics is controlled using a PIC microcontroller, which is shown in the centre, with its crystal oscillator just to the left of the PIC. There's a rotary encoder at the top. These work by sending a series of codes as the dial is turned. That way the encoder provides a signal showing its relative movement. I've created a separate video explaining how you can use the rotary encoder with the Raspberry Pi Pico. See the description for more details. The components shown using dashed lines either relate to the alternative potentiometer based version, such as the VR1 on the left, or and microprocessor voltage supervisor based around the MCP 111. The instructions say that in practice the voltage supervisor is not actually required, and so the components aren't provided for that, but there is provision on the PCB if one was added. There's a programmer interface header shown at the top. The switches in the centre are shown in the form of a keypad matrix. This reduces the number of pins required for the switches to 4 across the top for the columns, shown as the thick line indicating a bus, and the corresponding 4 pins to determine the row. I've written about how a switch matrix works in the Magpie magazine, but I realise I don't have that on my own website or YouTube channel, so I'll look at providing an explanation about how that works in future. Finally, the connector on the right shows the connector for the LCD display. Note that the display appears to share some common pins with the column inputs to the button matrix. Presumably this is to reduce the number of pins needed on the PIC. Presumably the data input to the display is toggled on when sending data for the display, and then off again when scanning the keyboard matrix. The final part is the PCB with the RJ22 connectors. This is known as a cab plug-in point, and a kit for this is included with the command station kit. There have been different versions of the board, and the PCBs for the old and the new kits are still available. The new PCB is a dual connector, but it can cut in half to create 2 single connectors instead. The kit comes with standard PCB terminal screws, but there are 2 sets of holes to allow pluggable terminal connectors if preferred. I switched these for the pluggable connectors, which made it consistent with the ones used in the command station. If you're connecting pluggable terminal connectors to both ends of the PCB, then one end should be on the top of the board and the other on the bottom. Check the orientation of the H and L markings on the connector so that they match that of the command station. Another thing about the RJ22 kit is whether to connect the terminating resistors. CBUS is based on CAN bus, a popular protocol used in automotive vehicles and various automation environments. I won't go into full details in this video. If you'd like to see more detailed explanation of how CAN bus works, let me know in the comments and I may try and follow that up in the future. The thing you need to understand when implementing the kits is the use of the terminating resistors on the ends of the lines. Being a bus technology, then effectively there's a single connection, or in this case 2 physical connectors due to the high and low wires. Multiple devices can then tap onto that connection. Then, ideally at the end of the bus, there should be a 120 ohm terminating resistor. These are needed as part of the signalling, but also being connected at the end of the path, they will reduce any signal reflection. In this case, with the bus being very short, would have been possible to use a single 60 ohm resistor, or typically 68 ohm to use a common E12 resistor value. But as I intend to expand my CBUS setting, I wanted to make it more future-proof. And so for the testing, I soldered one 120 ohm resistor to the PCB and used another 120 ohm resistor which I just connected to the spare pluggable terminal connector. When I complete my setup, I'll be using a CBUS connector board, known in the kit locker as an LCB connector board. And this will allow me to have one of the resistors on the RJ22 PCB, possibly on a different model railway module board, and one on either a separate RJ22 board or on the CBUS connector board. Finally, with the 3 kits fully assembled, it's now possible to test it on a real model railway. I replaced the bench power supply with a 15 volt DC power brick, again available from the kit locker. As I was connecting to an existing model railway, the first thing was to physically disconnect the railway from the existing DCC command station and then connect this new command station in its place. I plugged in the handset, entered the code of the DCC loco and it worked fine. The standard DC locomotives, I can drive it around the railway, and with the ones with the sound fitted, then I could select the appropriate functions which changed value whenever that button was pressed. So for example, pressing 1 turned on the sound of the engine for the class 24 diesel, and then turning the dial allowed it to move. With that tested, I now have a kit-built DCC controller. At the moment, it doesn't offer anything over what can be achieved from the standard off-the-shelf controller, although it does support accessories, whereas my Gauge Master Prodigy Express controller does not. It's going to be when I connect other devices to the CBUS when the extra functionality becomes available. So please subscribe to find out about the CBUS USB interface kit when I get to try that out. You'll also want to turn on the notification icon so you don't miss when I release the video. I think it's a shame the handset is so difficult to solder, as I think that may put people off, although hopefully with a bit of experience you should be able to get there. It would be easier if there was a pre-built or commercial handset and to use that in conjunction with the DCC command station, although I appreciate that MERG is about being hands-on, so it tends to use kits rather than pre-built devices. It's worth noting how friendly I found other members of MERG, and I'm sure that if someone is struggling with soldering, they could get support from their local group. That's it for now. The kit is up and working. I didn't have any major problems, although as I said, soldering the handset involves some more advanced soldering than typical kits. Thanks for watching. I look forward to seeing you in a future video.